not starting at 1 now, so now I'm starting at n equals 5. So I've got the sequence where my nth term is the square root of n minus 5. If I plugged in numbers less than 5, I would have imaginary numbers, which is fine. You can have a sequence with complex numbers. I'm keeping my sequence real for right now because we won't deal with complex numbers until later in the term. There's nothing wrong. I could have easily started at n equals 0 and gotten some complex numbers in my sequence. That would have been completely fine. There's nothing wrong with doing that. But if I want this sequence to stay a real sequence, I need to start at n equals 5. So again, here, if I'm just telling my reader in general what does a term look like, well, I'm going to tell my reader the formula for my term, which is a sub n is equal to the square root of n minus 5. And then I need to tell my reader, hey, how are we changing the index? So my index is for any n greater than or equal to 5. And again, go ahead and plug in 5. You're going to get 5 minus 5, or the square root of 0. Plugging in 6 will give you the square root of 1. Plugging in 7 will give you root 2, 8 will give you root 3, and so forth until we get up to the nth term, which is the square root of n minus 5. So my first term is 0, my second term is 1, my third term is square root of 2, my fourth term is square root of 3. Here I've got a sequence using a trig function, so I'm using sine. So I have sine of n pi divided by 4. So this is going to take us around the unit circle. So remember, if you're doing a trig function, make that unit circle for yourself so that you can go around the unit circle and ask yourself, what are my values? Or just go print a quick unit circle off the internet. There's lots of unit circles. Don't let not remembering trig functions be the thing, quick easy trig angles be the thing that trips you up on a problem. Here we've put n equals 0 because we want our reader to know that we're going to actually start at the 0 angle and not at the pi over 4 angle. That's when I put in n equals 1 as opposed to n equals 0. So I'm going to start at n equals 0. So again, a sub n is equal to sine of n pi over 4 for n equals 0 or greater. When I plug in 0, I'm going to get sine of 0. Sine of 0 is in fact 0. When I plug in 1, I'm getting pi over 4. And if you go back to your trig circle, convince yourself that sine of pi over 4 is root 2 over 2. When I plug in 2, I'm going to get 2 pi over 4, which is just pi over 2. That's when sine is equal to positive 1. Then we're going to get root 2 over 2 again, go back down to 0. Then we'll have negative root 2 over 2, negative 1. The next one would be negative root 2 over 2. It would then circle back to 0. I didn't need to do all that though, because in general my nth term looks like sine of n pi over 4. So this one, notice it's actually going to be cyclic, and it's going to rotate around. And this one seems like it's going to never really get anywhere. Whereas, say, this one is just getting bigger and bigger and bigger. And let's go here. I'm negative, I'm positive. I'm negative, I'm positive. I'm negative, I'm positive. Don't they seem like maybe they're getting smaller? Like that one definitely got smaller, and that got smaller. And 3/4, quantity-wise, 3/4 is smaller than 1. Quantity-wise, a half is smaller than 3/4. 5/16 is smaller than 1/2. What are these sequences doing? And that's one of the questions that we're going to ask in class. So what are the sequences doing? Do they look like they're converging? Do they look like they're diverging? I know you've dealt with limits before, so think about that sort of thing. Is this one ever going to get anywhere? All right, so not all sequences can be written explicitly as we did before. Some of our sequences can't be expressed using a formula at all, and some of our sequences are defined recursively. I'm going to give you the most famously defined recursive sequence as an example, which is the Fibonacci sequence. So the Fibonacci sequence looks like 1, 1, 2, 3, 5, 8, 13. Our next one up would be 24, so forth, so forth, so forth, or so I'm so sorry, 21, then 34, so forth, so forth, so forth. So how are we getting this? Because I don't see an explicit way to get there and just say, oh, the nth term is this because I have one, then I have one, then I have two. Even if I go, okay, well, maybe it's behaving weirdly. 1, 2, 3, 5, no, now it starts behaving weird. How is it behaving? So how it's behaving is actually in terms of how it behaved before, which is what recursively means. So what we have to do for the Fibonacci sequence, some recursive sequences you only have to define the first term. Here we have to define the first two terms. So we're going to use a sub naught just because that's traditionally how the Fibonacci sequence is defined, as the 0th term instead of the first term. Those sorts of things aren't the biggest deal as to how you're deciding to do things. The main thing is consistency. As long as you're explicit and consistent and you're letting your reader know what you're talking about, that's fine. You can start with the 0th term. You can start with the first term. So if we let the 0th term be 1 and the first term also be 1, then I can define any term after that in terms of the previous two terms. So the n plus first term is equal to the nth term plus the n minus 1th term. That is to say, how did I get 8? Well, I got 8 by adding 3 and 5 together. How did I get 13? I got 13 by adding 5 and 8 together. How would I get 21, which is the next number in my sequence? I would get that by adding 8 and 13 together. That's why I also knew 34 was the next one, because 13 and 21 will give you 34. So this is an example of a recursive sequence. Again, my recursive sequence might not require 2 terms. It might only require 1 term. Some recursive sequences require 3 terms or 4 terms or 5 terms to be defined, and it really just depends on the general formula. How many previous terms did the general formula need to be defined? And that's all you need to have known for what are the first couple of terms. Okay. So here's our final example. So again, I said that not all sequences can be explicitly defined. And in general, some of them can't be defined at all without just describing how they're created. So sometimes there's not a formula for it, and you just have to explain it. So here's an example of that. So we're going to define a sequence whose nth term is the digit in the whose digit is the nth decimal place of the number pi. So what does our sequence look like? It looks like 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8. And for those of you who have pi memorized up to some other digit can probably keep going, so forth, so forth, so forth, so forth. There's not an explicit formula for this because pi is an irrational number, and irrational numbers have no formulaic sequence to their digits. So this is explicitly an unformulaic sequence. There is no way to describe the numbers that we will get here other than the way that I've just described them above, i.e. the digits of the nth term being the digit of the nth decimal place of pi. Ooh, that's a mouthful. I could have also done something that maybe changes based on what we're seeing. So maybe my sequence is going to be the temperature in my house at 12 o'clock in the afternoon every day from here to eternity. Well, that will take a very long time to collect that data, but theoretically, if we could go to infinity and my house could last till infinity, then that could be an infinite sequence. And that's it for right now. So go ahead and take a look at the sequence activity before you come to class and see if you can try any of them. I know I didn't define a bunch of those things. I want to see how much you know before we go and do those things.